All right, this is the second video for A number 7, integration by trig substitution. And I thought I'd just take just a second to look over kind of the setup for the problems and how you can kind of get an idea of what triangle to set up. So in example 1, we did a problem that was 9 minus x squared, and the triangle that we set it up ended up having a sine theta in it. And in example 2, we had one where you had the integrand with a plus underneath the radical, and that ended up being a good setup for tangent, because this will end up being on the hypotenuse, and you've got the two legs here. The third case that comes up will be if you have the x squared first, minus the constant, and then it will be a right triangle where where the square root expression goes on one of the legs. And if you set this up, in this case, you'll end up wanting to use secant. And I'll tell you why, and it's because you want the whole reason of writing these three trig functions here, sine, tangent, or secant, is so that you can take the derivative of them and get your d theta. So the derivative of sine theta is cosine theta, d theta, and this side is easy to integrate. So I like that we're using sine for this, because the derivative of sine is positive, and having this be x over a is nice because it's easy to differentiate. So tangent and secant also have the fact that the derivative is positive, and you want the expression over here to avoid using the square root side of the triangle. So you'd have a choice here between putting the root on either leg, but if you put the root on the opposite leg, then your secant function is equal to the hypotenuse over the adjacent, and you end up with a function that's easy to take the derivative of and is positive. All right, so let's see that in an example. And since we haven't done a definite integral yet, we're going to go ahead and do that. So here's the integral that we're going to solve. And even if you don't have those triangles that I was just showing you memorized, which I wouldn't recommend trying to memorize them, I would look at this and recognize that it's a trig substitution problem because you have this radical in here. You might think a u substitution could work, but if you let u equal x squared minus 3, then your du is 2x, but it's in the denominator. So if this was flipped around, then it would be okay to use a u substitution, and you should. Don't do a more complicated integration technique than necessary, but in this case you definitely will need a trig substitution. So in trying to decide where to put the values, you might guess and check and get it wrong and have to guess again. So in this case, I know that one of the sides is x and one of the sides is going to have to be the square root of 3. Because of the subtraction, it's going to have to be the x here, and then I'm trying to decide between putting the root 3 here or the root 3 here. And it turns out I want it here. Because if it's there, then when I go to write secant theta is equal to r over x, I get x over root 3, which is good because I want the x in the numerator. I want to use secant because the derivative of secant is positive. And if you had switched this around, the x has to be here, but there's no good reason geometrically why it couldn't be written this way. But then if you used secant, you would get x over this, and you wouldn't want to take the derivative of this function, as you need the quotient rule and the chain rule. And you could get away with cosecant, but cosecant would be our hypotenuse over opposite. So that's fine. Oh, this is root 3, sorry. But then the derivative of cosecant is negative cosecant theta cotangent theta, and you may as well you do it this way so that you get to avoid having the negative in there. All right, so to get the dx to be replaced, I'm going to take the derivative of this. So the derivative of secant theta is secant theta tangent theta. And the derivative of this will be 1 over root 3 times dx. Oh, and I forgot the d theta there. And so this will be root 3 secant theta tangent theta d theta is equal to dx. All right, so that will take care of this. And then look around for a clever substitution to get rid of this, and I can see root x squared minus 3 over x is here. So I could say opposite hypotenuse. So the sine of theta is equal to and then this, because it's a definite integral, you're going to need to replace your limits of integration in order for this to be a equivalent integral. So these are x variables, so the secant of theta is equal to root 3 over root 3, which means that the secant of theta is equal to 1. If I take the reciprocal of both sides, that would be the cosine of theta is equal to 1, which happens at 0, which is great. So then this becomes, when I substitute it in root 3, theta ends up being 0. And if I substitute in 2, I get that the secant of theta is equal to 2 over root 3. So the cosine of theta is equal to root 3 over 2, which is pi over 6. The x is long. Comparatively, if it was the cosine equals 1/2, it would be the tall triangle. So then this is pi over 6. And then the integrand, the square root of x squared minus 3 over x is equal to sine theta. And the dx is equal to the square root of 3 times secant theta tangent theta d theta. And now we'll just clean that up and take the antiderivative and get to our answer. So the square root of 3 can come in front. It's supposed to be a 3. And this is 0 to pi over 6 sine theta, and secant theta is 1 over cosine theta, and tan theta is sine theta over cosine theta. And so this ends up being tangent squared theta d theta. Which gives me a little pause. Do I really know how to deal with that? I don't know an antiderivative that is tangent squared off the top of my head, but the Pythagorean identity is jumping out, saying pick me, pick me, pick me, and the Pythagorean theorem, the Pythagorean identity for tangent squared is secant squared theta minus 1. And I know the antiderivative of secant squared. That is just tangent theta. The antiderivative of 1 is theta. This is from 0 to pi over 6. And it's great to have changed these. One, it's required to change the limits of integration, but it also means that then I don't have to go back to x's right now, which is also kind of nice. So the tangent of pi over 6 is here. It's a short one, so it's going to have to be, instead of root 3 over 1, it's 1 over root 3, which generally we might write that as root 3 over 3, but since we've got that in front there, I like it as 1 over root 3, and then pi over 6, and then tangent of 0 is 0, and theta with 0 substituted in is 0. So I end up just distributing this. Root 3 times 1 over root 3 is 1, and this will be pi root 3 over 6. Sorry if I went off the screen there. All right, so that's the last example. These problems are kind of tricky, but also kind of a good puzzle and kind of fun. And I would say these are the hardest types of integration that would be covered in a calculus course. And what makes them hard is just recognizing what skill you should use to solve them, given that you've got a lot of choices. You've got U substitution, you've got integration by parts, you have partial fractions, and so it's just hard to know when you look at it to determine which integration technique you should use, and that's definitely one of the hardest parts of integration. What clues me in on this one is I would always try a U substitution first, but I can tell right away the pieces aren't in the right spot, and then because this has this kind of glimmer of the Pythagorean theorem in it, that's the clue that a trig substitution might work. So anyway, good luck. Thanks for watching.